Hello, everyone. Welcome back to my TCR-seq video tutorials. In my previous video tutorial, we loaded the demonstration dataset and combined the data. Today I'm going to show you how to perform basic visualization of clonotypes. So in this video tutorial, I will show you several functions to visualize clonotypes. So there are some general arguments among different functions. So we can introduce those arguments before we run different functions. So the first one is the clone call. There are four variables you can select from the clone call arguments. The first one is gene. Gene are the gene names for the VDJC gene names. The second one is NT. NT is the nucleotide sequence. And the third one is AA. AA is the amino acid sequence. And the last one is strict. So I showed you the data in my previous video. The strict will call the clone sequence for the gene names plus the nucleotide sequence. If you look at the online tutorial, sometimes they use gene plus NT. This will produce the same result as the strict variables. So in most functions, you can use four variables. The exception is when we use the length quantic function. In this function, you only can select NT or AA. I will show you later for this function. So the second common argument is the chain. We can use both the alpha and the beta chain, or you want to select an individual chain, for example, TRA for the alpha chain and TRB for the beta chain. And also, there's an exception with the genes function. When we look at gene usage using this function, you cannot select both as a variable. You can only select TRA or TRB. So the third argument is the scale. You can set it as false or true. If you set it as false, it will show the clone numbers. If you set it as true, the data will be scaled by the total number. The last common argument I want to talk about is the export table. The default setting for all the functions is false. If you set it as true, then we can export a table for the data generated by the analysis. So you will see how we perform those analyses in the following demonstration. So now we can use different functions from the SC repertoire package to visualize the clonotypes. The first one I want to show you is the abundance quantic. So this function can calculate the abundance for each clonotype from the demonstration dataset. So for the data analysis, I always want to see how the data looks like. So first we can set the export table as true in this function. Then we can generate a table to see the data. So for the abundance quantic function here, we can first set the clone call as amino acid, and the chain is both. Then if we set up the export table as true, then we can generate a data frame to show the clonotype abundance. So let's run. You can see we have a data frame here. We can click the data frame and have a look. You can see we use the clone call as amino acid. The chain are both. So we have the amino acid sequence for both alpha chain and the beta chain. Here is the clonotype abundance, and then the values are the sample type. So you can see the abundance for most clone types are just 1. We can connect the abundance column to see the clone types that have abundance more than 1, so we can connect it. You can see now the highest abundance in our dataset is this clone type, and it is in the third patient tumor samples, and the abundance is 482, and the second one is 285. It is also in the tumor samples. So later when we talk about top 10 clone types, that means we choose the top 10 abundance from each sample. So we use the clone core as amino acid. You can also generate a table, use the clone core as a nucleotide sequence we can run. You can see we generated a data frame using the clone core as a nucleotide sequence. We can try the clone core as a gene and also strict. You can see we use the different type of clone core, and the chain will be the same for both alpha and beta chain. But here you can see from the data frame, the number for the observations are slightly different. And also we can use the clone core as amino acid. Here we set the chain variable as alpha chain, TRA. Let's run. You can see now we generated another data frame for the alpha chain. You can see the number difference between both datasets. The top one is for both chain. This one is for the alpha chain. So we generated different data frames. So you know how to set the argument for clone core and the chain. So you can change the variables here for the clone core and the chain to make a different combination. Then you can see more data using the abundance quantic function. So we generated 5 data frames here. If you want to save those data frames, you can use write CSV function to save the data frame as a CSV file. Here I just show you use the data frame amino acid as an example to save one of the dataset we can run. So we saved this data frame as a CSV file in my computer. So because we set the export table argument as true, the default setting is false. So if we use the default setting for the export table as false, if we run the abundance quantic function again, then we can generate a figure to show the abundance for each clone type in different sample set. Let's run the clone core as gene and the chain as alpha chain. If we run, you can see we generated a figure here for 6 samples. We have the first patient, peripheral tumor, second patient, peripheral tumor, and the third patient, peripheral blood tumor. So the color difference indicates the different data set. You can see the x-axis show the abundance of clone types, and the y-axis show the number of the clone types. Because we use the clone core as genes, we can connect the data frame for the genes to see the abundance of different clone types. Let's connect it. You can see the abundance for most clone types are 1, some have 2. We can rearrange it to see the clone types that have the high abundance numbers. So this figure is for the alpha chain. You can also run the same function, change the chain to beta chain. So we generate a figure for the beta chain. Also, you can set the chain argument as both to see the abundance for both chain. You can see we generated another figure for both chain. So that's the first function for the abundance of clone types. You can change the clone type code to amino acid or nucleotide in combination with different chain to see how the figure looks like. So now I can introduce the second function, the quantic function, to quantify the clone type. First, we can set the clone core as strict. That will be the gene names plus the nucleotide sequence. And we can set the chain for both alpha and beta chain. According to the online tutorial, the strict variable for the clone core is the most specific analysis. So we can run this code. You can see we generated a bar chart to show the clone type numbers for each sample dataset. So the PY patient peripheral blood samples has the highest number of unique clone types. So next we can run the same code, but we set the scale as true. Let's run. You can see we generated another bar chart. But now it shows the percentage of unique clones, which shows the percentage of unique clone types for each sample dataset. In this analysis, the unique clone types number was divided by the total sample numbers from the same dataset. So we use the chain as both. If we want to see the unique clone type numbers for the alpha chain, we can set the chain argument as TRA. We run. Now you see the figure is for the unique clone types for the alpha chain. If we set the scale as true, we will see the percentage. We can run the same for the TRB for the beta chain, the total unique numbers, and also the percentage for the beta chain. So we run the quantic function to see the unique clone types numbers and also the percentage for each sample dataset. If we want to see the data that we used to generate those tables, we can set the export table to. Then we can get a table to see the numbers that were used to generate the figure here. So let's run this code, and here we set the scale as false. If we run, you can see we have a table here to show the unique clone types for each data sample and the total samples in this dataset. Here we use the clone core genes. If we set the scale as true, let's run. You can see now we have a data column as scaled to show the percentage of the clone types. So this percentage was calculated by the unique clone types divided by the total sample numbers. So in most situation, we are talking about the clone core chain argument. And in each function, you can also set a group by and split by argument. For example, here we can set the group by function as ID. We know the ID column shows the samples as peripheral blood or tumor samples. If we run, you can see now we have the unique clone types for the peripheral blood samples or tumor samples. If we set the scale as true, you can see now it shows the percentage of unique clone types. That means we divide the number for the unique clone types by the total sample numbers. In the first video, I showed you that the data for each sample has NA values, so we can use the check quantic function to see the percentage of NA values in each dataset. For example, here we can set the chain as alpha chain, and we examine the genes, and we can set the group by function as samples. Let's run. You can see because we examine the genes in the alpha chain, we only have the VJC genes. You can see the MV values distribution in different genes. And here the color indicate the different data set. And also we can check for the beta chain. Then we can set the chain argument as TRB. We can run it again. You can see now the beta chain has 4 genes, V, D, J, C. And you can see in the beta chain, the D genes have very high NA values. So next we can use the length counting function to check the length of the clonotypes. Here, this is the exception that we can only set the clone code as amino acid or nucleotide. So for example, we can set the clone code as amino acid and the chain as both. Let's run. You can see we generated a figure. Let's zoom in to see the figure more clear. You can see the x-axis is the length for the amino acid, and the y-axis indicates the number of CDR3 amino acids, which is the total number for the same length of amino acid in each sample dataset. So here is the amino acid. We can also set a nucleotide for alpha chain. You can see here is the length for the nucleotide, and here is the total number of the same length of nucleotide in the alpha chain. We can run another example as the clone code for amino acid, then chain as the beta chain. If we run, we generated a figure again. As I mentioned, in this function, you can only use the amino acid or nucleotide variables for the clone code. If we set the clone code as gene, let's run to see what it could happen. We run. You can see now we have an error because we cannot set a clone code as gene or strict in length counting function. So I showed you 4 functions already to visualize the clonotypes. So next we can use the function compare clonotypes to compare the clonotypes between different sample types. So in order to see clearly what's going on in the figure, we can just set the numbers as top 10 clonotypes. This is the top 10 abundance for each sample type. So here we are going to compare the samples between peripheral blood and the tumor samples in the first patient. The clone code we can use the amino acid, and we use the Vonnegut package to generate the graph. So let's compare the top 10 clones for the first patients between peripheral blood and the tumor samples. We can run, and we generated a figure. Let's zoom in to see the figure. You can see here we use the clone code argument as amino acid. So here show 15 top clone types. Because we choose the top 10 clone types from each sample, the peripheral blood and the tumor samples. So there are some overlaps between the top 10 clone types. So in total, we get 15 here. You can see on the left-hand side, we have 11 clone types here. That means we have top 10 clone types for the peripheral blood samples, and then one clonotype that belongs to the top 10 clonotype for the tumor samples. You can see in this patient, we can find all top 10 clone types in the tumor samples. On the left-hand side are the top 10 clones for the tumor samples. Also, some clone types that belongs to the top 10 clones in the peripheral blood samples. So you can see from here, 3 clone types down here are tumor specific. We cannot find it from the peripheral blood samples. So this figure is for the first patient. We can also run the same comparison for the second patients for the peripheral blood and the tumor samples. Let's run, and we can zoom in. You can see here are the combination for the top 10 clone types in the peripheral node samples and the top 10 clones in the tumor samples for the second patient. You can see in the second patient, there are 6 clone types we cannot find from the peripheral blood samples. So we compare the top 10 clone types for the second patient. We can run the same function for the third patient. Let's run and zoom in. You can see in the third patient, there are more clone types we cannot find from the peripheral blood samples because the tumor samples from the third patients are in the later stage of tumor development. So that's why in this tumor we have more tumor-specific T-cell clone types. So you can see this function is very useful to compare the clone types between different sample datasets. So the last function I want to introduce to you in this video tutorial is the with genes. This function we can realize the gene usage. So in this function we can set the gene argument as V genes, D genes, J genes, or C genes. If you decide to set the D genes, this gene is only presented in the TRB beta chain. So here, if you set a gene as D, then the chain you have to set it as TRB. Then the plot argument we can set as bar or heat map. I'm going to show you later how to use the heat map argument. And the order you can set the variance for the order or set the gene names as the order. And the scale argument is the same as above functions. If we set it as true, we will divide the gene numbers by the total samples. So we can run this code to demonstrate the gene usage function. Let's run. Let's zoom in to see the figure. So here is the bar chart for different patients. Because we set the scale as true, so the number on the y-axis is the gene usage number divided by the total sample number. So here we use the bar chart to show the top 50 genes that are presented in the 3 patient samples. You can see the first gene is TRBV20.1 gene. It has the highest usage in the third patient. Then the second gene is the TRV28. It has the highest usage in the first patient. Then the third one is the TRV2. It has the highest usage in the PY patient. So here we set the scale as true. If we set the scale as false, then the y-axis will report the raw numbers of the gene usage. Let's run. You can see now the y-axis changes to the numbers of the gene usage in 3 different patients. So we use the plot argument as a bar in both demonstrations. You can also use the plot argument as a heat map to see the gene usage in different patients. So we can demonstrate in this code that we set the plot as a heat map, and we are going to use the gene as J here. Let's run. You can see we generated a heat map. Let's zoom in again. You can see the high usage of this gene, the TRAJ42 in the third patient, and the second highest usage is this gene, TRAJ39, in the first patient. In this demonstration, we set the scale as true, so here is the scaled value. If we set the scale as false, we will generate a heat map to show the total numbers for the gene usage. You can see now we changed it to the total numbers. So using this with gene function, we can also compare the difference. For example, we are interested in the V and J gene usage between tumor and peripheral blood samples. Then we can select the samples for the peripheral blood. The sample will be 135. Then we can set the gene as V, chain as TRB. The y-axis, now we set it as J. Then we can compare the gene usage for both V and J gene in the TRB chain. So we are going to plot it as a heat map first for the peripheral blood samples. Let's run. So here you can see we set the scale as false. Then we have the total numbers for the gene usage. In the peripheral blood samples, you can see now the x-axis is the V genes and the y-axis is the J genes. You can see the TRBJ21 gene and the TRV gene 101 gene has high usage in the peripheral blood samples. The next we can set the same set of code, but we select the tumor samples now, because the tumor samples are 2, 4, and 6 in the combined dataset. Now we can run for the gene usage for the tumor samples. Let's run. So here is the heat map for the V and the J gene usage in the tumor samples. You can see the TRBJ223 and the TRBV2021 has the highest gene usage in the tumor samples. Okay, I showed you how to use the basic function from the ESC repertoire package to visualize the different clonotypes. I'm going to stop from here today. In my next video, I will show you how to perform advanced visualization of clonotypes using this demonstration dataset. So please subscribe my channel, and I hope to see you in my next video tutorial.